Welcome to everybody. Today we're talking about the shear in open section beam, especially for thin walled beam. Closing the lectures related to the bending moments, today we switch on the shear, in particular for the open section beam, and we're going to derive a certain formulation to calculate this shear flow. So we have here two images, 17.1 from Megson books, and on the other side in a generic shape of a beam. So a thin walled beam is called so because the thickness of the wool beam is less than the height of the beam and less than of the other geometrical quantity that represent our beam. In this case, B stay, for example, the base of the beam. So this beam is very low that I can negligible this quantity. So the power of the thickness are negligible because T is very low. The T at square power is a number very low. This is one of the hypotheses that we must make for studying this open section beam and shear in this particular beam. So, but first to introduce anything, we introduce the hypothesis for the shear in open section beam. The first hypothesis is that the axial constraint, the effects of axial constraint are negligible. The shear stress normal to the surface of the beam can be negligible. The beam is a thin walled beam. The shear stress that are acting, the shear stresses that are acting along a normal plane to the surface of the beam can be considered constant along the thickness. The same beam is formed by a constant and uniform shape. So this image, this drawing can help us because this is a beam, an E-shaped beam. In the section along the z-axis, zeta is the longitudinal axis of our beam, so this is the axis Z. I can make this axis with another pen, let's say orange pen. This is our x-axis. Okay, so in section 1, section 2, section 3 we have the same shape, in this case the E shape, but locally around any shape the thickness can be vary. But if I think the wool beam, the distribution of the thickness is constant, but the variation locally around the single shape at station 1, station 2, station 3, station 4 and so on is very low, and so we can clearly say that the distribution along the same shape can be reasonable, considered constant also locally. Obviously along the beam the distribution of the thickness is constant, but with assumption that thickness has a very short variation, so I can say that also locally the thickness can be considered constant. So the total assumption that we made is that the thickness is constant along the beam. So we see from the figure 70.1 two pieces of the same beam. In the figure A we see the shear stress, so that are the tau zs, that is equal to tau zs, is similar to the discussion of the tau xy is equal to tau yx, for example. So I can here's this. So we see also the dimension of this piece of the beam. So as a length delta s, and the other length is delta z. the Z and S. S is a particular axis. We will see. We're going to see that S is an opportunely chosen abscissa, but in this case is a simple axis, so that give us the positive direction of all the bending stress, or the bending stress or hoop stress along the S direction. So this is the direction of the positive sigma S, tau zeta S, and sigma S. So this is the positive direction for example sigma Z and tau S zeta. So, but when we talk about of the I can move this stuff here. When we talk about of the an open section beam clearly, but a thin walled beam, the most simple thing to do is talk about of the shear flow. So the figure B, where we see the direct stress that are sigma Z, and the shear flow that is Q. Q is the shear flow, because the shear flow is equal to the shear stress times the thickness. In dimensional analysis, we obtain that this is tau is equal to Newton divided by millimeter at square power times millimeter for the thickness, and so we have that Q as a unit of measure that is equal to Newton divided by millimeter. Okay. If the thickness is constant, this is the powerful of the first hypothesis that we made. If the thickness is constant along the beam, I can switch from shear flow to shear stress simply using a fraction. So Q divided by T is equal to tau. Stop. So this is the simple thing to do. Clearly, sigma Z is the bending stress produced by a pure bending or produced by a shear load, because the bending stress can be produced also from the shear loads. Sigma S, that is this, is a hoop stress, but for our consideration, the other assumption that we can make that sigma S, the hoop stresses, are equal to 0. This stresses is related to an internal pressure internal to the beam, but for our consideration this quantity is equal to 0. We can write the equilibrium equation of this piece of beam along the zeta axis and S axis, taking into account the figure B. So along the zeta axis we have this quantity here and this quantity here as direct stress. So we have sigma Z plus d sigma Z over dz multiply dz. Now this is a bending stress, so and stress derived for due to a shear load here as sigma Z. So I want to obtain a force that are acting along the z axis, so I can take into account this area here, because this is dimensionally is Newton divided by millimeter square. To obtain a force, I must multiply by an area. This area is clearly this area highlighted here with the red pen, and that is this area is equal to T times delta S. This is the area. This quantity here multiplied by the area gives us a certain force. So the other quantity is minus sigma Z, because as you can see here, sigma Z is direct in the opposite direction of the positive zeta direction. So it is sigma Z times T times delta S, because it's the same area that we calculated a few minutes ago. Now the other quantity to take into account along the zeta axis is this quantity here, this shear flow here, and this shear flow here. This shear flow is direct in along the zeta positive axis, so we have plus Q plus dq divided by the S times ds, and the other shear flow is directly in opposite direction, so it's minus Q times ds. Okay, so because clearly I made an error here, I must multiply times dz, because, and here we have Q times minus Q times dz equal to 0, because I must multiply dz, because is the clearly this is the quantity dz, the side, the edge where this shear flow is acting is as a length equal to dz, as you can see. If I here's this, as you can see from here, this is the dz edge. So Q as an unit of measure Newton divided by millimeter, multiply by dz, we obtain a force. All these equation must path equal to 0 for the equilibrium. Along the s-axis we obtain a similar thing, that is so this is the equation for the equilibrium along the s-axis. We derive the equilibrium along the zeta axis, and then for analogy along the x-axis. So if I made some calculus, I can obtain these. So this quantity here can be we can simplify this quantity here, plus and minus Q delta Z, and we obtain finally that along the zeta axis the equilibrium give us this equation, that is, I write here, that d sigma z divided by dz, ds and ds are simplified, and we obtain also dz are simplified, so the sigma z divided by dz times t is equal to minus dq divided by ds. Okay, this is the equilibrium equation along the z-axis, and also the equilibrium equation is the sigma z divided by dz tau plus dq divided the s is equal to 0. This is the equilibrium equation along the z-axis. The other equation I don't derive, because I say that if you made some calculus, we obtain d sigma s divided by ds times t plus dq divided dz. But I said as a hypothesis that the hoop stress are equal to 0, and so the equation, the equilibrium equation along s-axis is not, we don't need this equation in this case, because the hoop stress is equal to 0. The equation to use for the open section beam to derive the shear flow is this, clearly along the zeta axis, that is d sigma z divided by dz times t plus dq divided by ds is equal to 0. This is the equation to where we want to start. We have reached this equation also here. So we have a general shape of a open section here from the figure 17.5 that is similar to the channel shape. So the channel shape is a open section beam, while an E-beam is an closed section beam. So it's clear because here we don't have the continuity of the beam. So the E-shape is a beam that has a certain continuity. Here, also here we don't see any continuity. We have a certain C, and here we have nothing. So it's open clearly. Now, because I reported also the figure on the right side, that is the 16.14 for the equilibrium of beam elements supporting a general force system in the YZ plane, because we start to derive the formula for the shear flow, and we also seen from the previous videos that sigma z, the bending stress due to the poor bending moment or due to shear loads, is equal to this general formulation. So this is the general formula. This is the second formula. This is the general formula of the sigma z. This is the first formula. This formula we know all of this formula. Now, if I have the sigma z to dz, clearly I must make this derivative. So the sigma z divided dz is the clearly this is a derivatives of a ratio of a fraction that we can write. So the call this. I try to refresh your mind of this. If hx is a certain function, we have fx of gx. The derivative of hx is the derivative of this ratio. Okay, so we have the first function f, the derivative of first function f prime of x, times the second function minus the function fx times the derivative of the g function x divided by the gx at square power. So this is the general formula to derive the clearly the derivative of a ratio, because the sigma z is a ratio of a function. We have a quantity at numerator that depends to the z and other quantity that don't depend from z. So if I made this calculus, for example, for instance, for the first member, so for all these first member, I have the first quantity derived, f prime of x times gx in this case is equal to, the first derivative is all these multiplied times x plus my xx minus mx xyy times the x divided by the z. All these clearly we have, but my board don't go on the left, we say multiply all these quantity here is multiplied for the function gx, that is ixx iyy minus iy at square power. All this quantity here is divided by ixx iyy minus ixy at square power. So sorry for that, but my board don't have a problem, don't go on the left, so I so say this is the curly bracket. We have this, okay, all this quantity here is multiplied for the, so as f prime for gx. If I made the other function derivative, that is fx times j prime of x, dt is this quantity, so curly bracket, we have the, this is here, multiplied for the derivative of the gx, that is the xx over dz iyy plus xx the iyy divided by dz minus 2 dx axy dz, curly bracket. Clearly we have certain things that don't depend from the z. Clearly all the moment of inertia, so this quantity is equal to 0 because not even depends from z. This quantity is equal to 0. Also this quantity here, because is x divided z, x z is z. So we obtain from the first quantity only this quantity here, so the my divided by the z ixx minus the mx divided by the z ixy times x. So the other quantity here, all this quantity here, is equal to 0 because multiplied by this 0, all this is 0. Now all this divided by I have this other quantity minus this other quantity. This other quantity is fx times j prime of x. But this is equal to 0, this is equal to 0, and this is equal to 0, because all the product of inertia and all the moment of inertia are 0. Because we have a multiplication to do, we have this all multiplied, the first term, all the first term multiplied by a 0 value. So we have here 0. Clearly, I lost a piece, that this curly bracket, this quantity here I made right here, ixx iyy minus ixy at squared minus clearly 0 as said before, divided by jx at the square power, that is ixx iyy minus ixy at square power, all at square power. So we can simplify this quantity with these two, and we obtain finally for the first member, so the sigma z divided the z first member, you obtain the my divided the z xx minus the mx divided by the z ixy times x divided all this quantity ixx iyy minus ixy at squared. So now we have to do the same thing for the second member plus all this the other calculation, but you know that if I made also the other calculation, the time for the video increasing a lot, so you can make this calculus. It's simple to make this calculus. Now we can see this, the derivative of my with respect to z, the mx with respect to z. Now is important this figure here, because we want to derive something. So for the equilibrium, now if I look this image, I want to derive the relation between the shear and moment. Now for the equilibrium of this piece of beam, we have, so clearly here we made some same consideration of x. X now is the x-axis enter in your screen. So if we see this from this point of view of x is entering in your screen, we see also a counterclockwise mx. So mx is negative, and mx also bend the upper fiber. If the upper fiber are bended, the moment is negative. Sy, the shear force, is negative because it's direct along the negative axis of y. So we obtain the other side is direct in positive direction of y. So we have Sy plus the Sy divided the z plus Wy is the distributed load that is direct along the positive y direction. So we have y times the z because we obtain the force in this case, no, as a distributed load where we do q times the length of the beam to obtain the lamped force. So wy times dz to obtain a force here. So the other side we have minus Sy, that is equal to 0. So if we make some calculus, we obtain clearly Sy and Sy can be simplified, and the sy, the z, dz plus y wy dz is equal to 0, and we obtain that y, the distributed load, is equal clearly minus the sy divided by the z. This is the let's say third equation. But if I refer to point A, to the equilibrium, to the rotational equilibrium, we obtain this moment here around M produce a moment that is clockwise, so is positive. For our convention, we obtain this mx plus the mx divided by dz delta z. So we have also the shear here that produce a moment around A point, and the moment produced is counterclockwise, so is negative. Sy plus sy divided dz delta z delta z okay, times dz, all times dz, the arm delta z. Also the wy, the Lambda force applied here, produce a moment around A point that is counterclockwise, is minus wy times dz for this arm here, that is delta z over 2. So we can write the z at square power divided by 2. And the other stuff is this moment mx that is counterclockwise, and so is negative, minus mx equal to 0. Making some simplification due to this quantity here is negligible because it's the length delta z that is infinitesimal length at is a very low value. At square power is very low yet. So this approach to 0. Also this quantity here, delta z times delta 0, all this quantity here approach to 0, but we save this quantity, minus sy times delta z. Here we have mx, with mx can be simplified, and we obtain plus the mx divided by z times dz equals minus sy times dz equals to 0. So we obtain that sy is equal to the mx divided by the z. So you obtain this relation. The fourth relation, so link the shear force to the moment. So as we expected, the shear is the derivative of the moment along z-axis, in particular the derivative of the moment that is acting around the x-axis divided by the z. So sigma x instead is equal to the my divided by dz. So now I can substitute this quantity obtained now in this formulation here to obtain finally that the sigma z divided the z is equal to. So we obtain the fifth equation. Now we can see the variation of the bending stress due to the shear loads, because we have shear now. So the variation, the bending stress along the z-axis is produced clearly depends from the shear Sx that is acting along the x-axis, and Sy that is acting along the y-axis. This formulation is quite similar to the sigma z studied for the bending moment. Now, from the previous equation, from the first equation, so these lecture are a little bit complicated because we start from an equation, derive another equation, so we go on again at the top equation. So from the first equation, we can clearly write that dq divide the S is equal to minus T the sigma Z divided the Z. We obtain this quantity finally, so the Q divided by the S is equal to all this quantity here minus T multiply SXX. So this is the sixth equation that link the variation of the shear flow along the S, that is our shear axis, or the opportunely chosen abscissa, and that we'll see clearly this consideration during the next exercise. And if I integrate this equation from the origin of the abscissa 0 to S, that is the length of our abscissa of the Q divided by the S times the S, I can derive also the left hand side, but the thickness is constant, X not is constant. Why not X constant? Because are the coordinates of our point, but Sx and the moment of inertia, product of inertia, are constant. So I can write this thing. So this is the seventh equation, that if I choose this abscissa such that at certain point we have Qs at 0, the shear flow is 0 at Qs equal S1 equal to S1, for instance, equals to a certain value n, I can write the seventh equation as we can imagine as Q at S equal S1 minus Q at S equal to 0 equal all this stuff that are right here. So this quantity we can report just here. So, but at S equal to 0, the shear flow is 0, so I can write an expression Qs for the shear flow that is equal clearly to all this stuff here. So Qs is equal to this whole quantity here. We have shear and product and moment of inertia, thickness, and X and Y. So now X and Y are the coordinates of the point related to the in this case of the portion of the section of our section that we are taking account. So for example, in the next video we will see the zeta section. So if I choose an S, this is my coordinate S, so my abscissa, opportunely chosen abscissa. Here is 0, and here is a certain value. I must derive an equation along the X, an equation along the Y direction. If this is X direction and this is Y direction, so along the Y direction, clearly the portion of the considered section is this, if this is the centroid. Okay, from the centroid is clearly the distance of this portion of the section from the centroid. This is Y. Okay, Y is placed at so the edge 1, 2 of this section is placed at certain value of Y, and is this value Y here, this Y. But along X, how vary the equation? So I clearly I must write an equation along the X, this, because this is X coordinate, but this is also the x-axis. So I can write that when x1 is equal to 0, when x1 is equal to let's say if this is this quantity is all this is length is equal to h divided by 2, when x1 is equal to minus h divided by 2 because it's on the left side of x, then s1 is equal to 0. When x2 is equal to 0, this is 0 of the x, the origin of the x-axis, then s2 is equal to h divided by 2, all this length. So we obtain the classic formula x minus x1 divided by x2 minus x1 equals to s minus s1 divided by s2 minus s1, and we obtain x minus plus, in this case, h divided by 2, 0 plus h divided by 2 equals to s minus 0 divided by h divided by 2 minus 0. If I solve this equation, we obtain h divided by 2 times x plus h at square power divided by 4 is equal to s times h divided by 2. I solve for x is equal to, this is the equation of the two paths in this integral here. This x is equal to, because is the variation along the x of the abscissa s. So when s is equal to 0, h is equal minus h divided by 2, this quantity here. When s is equal to h divided by 2, x is equal to 0. So s, this coordinate here, this abscissa here, varies from 0 to h divided by 2. So s varies from 0 to h divided by 2. So we obtain an equation along the x-axis. We can say the equation of the x in function of s to path to in this integral. So this video is quite long as always, but I hope that is all clear as explanation, and so we will see in next video for the explanation of this exercise of the zeta beam. Bye.